No, wait, go. Wait.
Okay. Well, welcome back to the MVP seminar. Today is also OCIE seminar. And today we are very happy to have Paul, it's Levy Oliver, Levy with us. And he's going to tell us about truth and in mathematics and the dangers of skepticism. So please, Paul.
Thanks, Jose, and thanks very much to for Marco and everyone for inviting me. First of all, it's a great pleasure both to see people that I've known for many years, like Drew and Alex, and it's also a great pleasure to talk on this work, which is really a new departure from me. I haven't given this kind of talk before at all, so yeah, great. Okay, so this is the I put the slides on my webpage already. So if you just go to the sort of paper manuscript of slides, if you go to the slides, you can see them there. And there's a URL over there. Maybe somebody could post it in chat for all the many people who are online. Right. Okay, so I thought I would, so there's 8 sections. I thought I would at least have a couple of minutes between each section and maybe a big break between 4 and 5, because I know I've got 2 hours, 50 minutes. So it's not so, it's only 75 slides, which seemed right for the duration that I've been assigned. Okay, well, there are some bits that I can skip if we really run out of time. But...
Only 2 hours, 50 minutes? No, we discussed it more. 4 hours.
4 hours.
4 hours. Otherwise, we do not pay you the.
Okay. Hello. Right. So, okay, I want to start off with just a sort of one slide summary of the point that I'm trying to get across or persuade you of, with maybe even successfully in this talk. So what I want to say is that when we think about maths, we have a certain amount of freedom to decide how credulous or skeptical we're going to be. It's not completely determined. I'm trying to be quite pluralistic today. It goes against the grain for me, but I'm trying, right, to be pluralistic. So there's lots of different positions, so a few different positions that I can allow. But and how do we decide between these different positions? A couple of things based on how strongly we feel the strength of our intuition and how cautious we want to be. So that's really it. Not that you might say not very philosophical things, just more kind of emotional. But that kind of would determine how credulous, where we're going to pick along the spectrum that I'm going to say. However, we don't have absolute freedom. There are certain constraints that I think we should follow. And one is this one. The really sort of the central, the sort of the moral of the talk is that our beliefs about, first of all, what about reality, mathematical reality. We're going to talk quite a bit about that. Bivalence of sentences, choice, like axiom of choice, that kind of choice, and consistency of theories. All of these 4 things, our beliefs should be lined up. They should be aligned with each other. So what I really want to avoid, what I'm not happy with, is the idea that we can believe that all our favorite theories are consistent, while at the same time thinking that they are not describing reality. So consistency of everything and reality of nothing, that I think is not an option. And hopefully I'll be able to persuade you of this. So another way to put this is that the price of reality skepticism is consistency skepticism. We don't believe in reality, we also going to lose the theories. And there's a qualification here. Can I get rid of this thing at the bottom?
Yes,
no, that was a mistake. Oh well, never mind. View, what was it? Full screen? Okay, right, yeah, it seems to have worked. Okay, so there is a bit of a qualification that there are some situations, some certain philosophical viewpoints that I'm okay with. You may be able to establish consistency by some other method without believing in reality. But generally speaking, this is, if you don't believe in reality, you also have to doubt consistency. That's the case I'm making. I want to.
What do you know by what do you mean by consistency of everything?
Okay, when I say,
and
I mean,
non-A cannot
consistency
be
of our
equal.
favorite theories. I mean, I don't need literally everything. It's a, yeah.
Okay.
Yeah. So, but I also want to say, the things I'm saying in this talk, they're not, okay, I would argue that they're not particularly new or radical. I mean, in the paper, I've got lots of quotations from the different points, many of the different points that I'm making, saying that many people have made the same points before, maybe not line them together into a story the way that I'm doing today, but generally, they're not that original, right? And I mean, obviously that doesn't mean that you have to agree with it, but it does. But I just say that this is not some kind of new or radical philosophy. Okay, the theories that are going to be mentioned, there will be a few more, but the main theories in this story we have. So you may be familiar with some of these theories. So piano arithmetic is a theory of natural numbers. Bigger than that, we have second order arithmetic, which is a theory of numbers and sets of numbers. It's a two-sorted theory. Bigger than that, we have third order arithmetic, which is a three-sorted theory. Talks about numbers, sets of numbers, and sets of numbers. And the biggest is the Menno-Fraenkel, which is a general theory of sets. So these are some of the theories that we will talk about today. I'm going through some kind of mathematical preliminaries here. You may well be familiar with a lot of this already. I just want to go through some preliminaries. So two kinds of choice that I want to talk about. So say that a relation okay. Okay, so let's say that a relation is entire when every element of the domain has an image. So the axiom of choice, one way of saying it, is that given any entire relation, there's a function contained in it. Okay, that's for function. There's it for functions. There's another kind of choice called dependent choice, which is often discussed. And that's for sequences. So if you've got a relation from a set A to itself, and an element of that set, then there's a sequence that starts off at A, and then each element is related to the next one. So intuitively, you're kind of picking one element of the sequence at a time. And axiom of choice implies dependent choice. So dependent choice is a weak form of choice. Okay, a famous theorem, perhaps you could say one of the most shocking theorems, many people would say, in mathematics, is the Banach-Tarski theorem that says that one unit ball can be transformed into two unit balls by splitting it into 5 subsets and rigidly moving each of the 5 subsets. Obviously, these are not measurable subsets, right? This is provable in ZFC, but if you've only got dependent choice, it's not provable, assumed as some consistency hypothesis. Okay, so this is a very old theorem from about 1900 something. Okay, going on. I'm just going on through the mathematical preliminaries, so hopefully nothing is controversial yet. So I'll write 2 to the nat for the set of all bit streams. So here's an example of a bit stream. Continuum hypothesis says that every uncountable set of bit streams is in one-to-one, can be put in one-to-one correspondence with the set of all bit streams. And we know from various people that it's impossible to prove and impossible to refute the continuum hypothesis in ZFC, provided it's consistent. And if you instead work with ZFC with large cardinals, or this is imprecise, of course, I've not said define large cardinal hypothesis, but they do. There's many kinds of large cardinal hypotheses will not change this situation. So it's quite a robust result.
The word bit stream is usual in England, I think.
Well, amongst computer scientists.
Scientist, fantastic. I needed that is a word. Now I know that it exists. Very good.
So based on, I mean, I could have talked about reals, but I find the bit streams a bit more natural for this setting. But whatever. You could use reals if you prefer. Anyway, in light of these theorems, it seems to be unknowable whether this statement is true or false. Now, it is true that some people, including Hugh Woodard, who spoke here recently, well, particularly him, have advocated principles that either entail CH or entail not CH. But these are controversial principles. They're way beyond the scope of this talk. They're also beyond the scope of my expertise. I don't think that the fact that he's advocating these principles really changes the points that I'm making. Okay. He is actually pushing for a particular answer to continuum hypothesis, so that's that's not the view that I'm arguing, that I'm raising a problem with. So let me say, that's some facts. We've been through the mathematical facts. That's pretty much it. There's not going to be much more maths in this talk. Actually, pretty much everything I'm saying in this talk could have been said in the 1920s before Gödel, right? There's nothing based on any kind of recent maths. And so here are two beliefs that I'm going to call them classical. And here this one belief is that the continuum hypothesis is bivalent. Bivalent means either objectively true or objectively false, right? The word determinate is sometimes used. I think I prefer bivalent. Maybe you will see why in the very last part of the talk, but never mind. If you prefer determinate, it will do. The point is it's saying that CH is either objectively true or objectively false. And this has nothing to do with knowability. We can be completely pessimistic and say that it's absolutely, it may be absolutely unknowable. But even so, it has an answer. There is a fact of the matter, whether it's true or false. And that is a classical belief about the continuum hypothesis. The other classical belief is that the axiom of choice is true. So these are two classical beliefs. But of course, as we know, foundation of math is a very subject where there are many different opinions and attitudes and many arguments. So here are two alternative views that are not in line with the classical one I put out. So the first one is that there is no canonical universe of mathematical reality, but there are many universes and they all of equal status, not one special one, but many that are equal status. They all satisfy the ZFC axioms, but some of them satisfy CH and some of them don't. They have equal status. There isn't one special canonical one, right? That's one view. You may have heard this view. It's quite popular in some circles. Another view, again, popular in these are two completely different communities that would say these things, but they would probably object to being lumped together like this, but never mind. Is that the axiom of choice is unacceptable because the Banach-Tarski theorem is so clearly wrong. Therefore, we should go down. Instead of working with ZFC, we weaken it to ZF plus dependent choice, where you don't have this problem, right? Again, I can think of some distinguished people who have advocated this. There are variations also, but people may say that it's kind of optional whether you want axiom of choice or whether you want axiom of determinacy, which contradicts choice. It's whichever you prefer, right? So but I'm just taking this. But what these views have in common, this is the issue that I don't like about them, and I'm going to argue against. So on the one hand, they're promoting a strong theory, at least ZF. They're not going for some very weak theory of mathematics. They're at least accepting ZF as our foundational theory. But at the same time, they're skeptical about this classical view of reality. It's this discrepancy which I really want to draw attention to. And my thesis is saying that this is having our cake and eating it. We can't, on the one hand, be skeptical of reality and still have a strong foundational theory. So to make this a bit clearer, so these two statements that I mentioned, continuum hypothesis and Banach-Tarski, they are third-order arithmetical statements. If you think about it, all the quantifiers in these statements, they only talk about natural numbers, sets of numbers, sets of numbers, nothing else. So actually, I find it a bit funny sometimes when people are talking about CH, they talk a lot about ZF, but ZF is far too advanced if you just want to talk about these two statements, right? they're just third order arithmetical statements. So really, we just need to think about the theory of third order arithmetic if we want to, when we're thinking about the status of these sentences. And so that allows me to formulate, if you like, the headline of my thesis, which is, if we are going to doubt the bivalence of continuum hypothesis or the truth of the axiom of choice, or to the extent that we doubt those things, we should also doubt the consistency of third order arithmetic. It's the same level, and that's for axiom of choice. If we even doubt dependent choice, which of course is even more skeptical, because dependent choice is a weak statement, then we even have to doubt the consistency of second order arithmetic. That's another part of this, but this is the headline, because as I say, there are two communities that are really doing this. And I am saying that they need to pay this price, right?
Any of us doubt about the consistency of zeta 2, no?
Haven't?
Any of us doubt about the consistency of zeta?
Well, if you're going to doubt all the consistency, then you're paying all the price up front. So then that's fine. I'm happy. I'm happy with that. If you're going to doubt the consistency of all the theories, then fine. That's not what I'm criticizing, so it's fine.
Okay, good.
Okay, I also want to say, now, it might sound like I'm criticizing communities who do mathematics without choice. That's not really the case. It really depends on the reason, right? So in some parts of math, like topos theory, people will avoid axiom of choice and other principles like excluded middle, but the reason they're doing it is to get information about interesting models, like certain toposes, where those principles don't hold. And people doing that, they can still believe axiom of choice to be true in reality. In fact, some of the papers, I mean, I've cited one paper where, you know, they are even using the fact that axiom of choice is true in reality. It's just not true, definitely not true in the particular models that they're studying. That's not a problem, according to the point of view that I'm doing. So I want to be clear that I'm not criticizing that body of work in any way, right? It's only the philosophical attitude that I'm criticizing, not that piece of maths. Okay, I think, yeah, right. Well, that's the end of the first part, and I promised that I was going to have a 2-minute break at least between each of these sections. So, that's it. So okay, get a break for 2 minutes. Maybe so, I don't know. I haven't really said anything yet. I mean, I just said what I'm going to tell you later. Yeah. Go on.
So sometimes you use the language objectively true or true in reality. So like, what are those modifiers doing versus just saying true?
I guess that I think I would be happy with just saying true. Well, okay. For the people who take this view, this one, right? They would say, well, true in one universe, true, but false in another universe. So for them, objective is perhaps making it clear that it's one universe, perhaps.
What if I think it's not resolvable in this universe, right? So it's unknowable in maybe
So remember, the classical view, the way I'm formulating it, is not claiming anything about knowability. It's perfectly happy for you to take the view that the truth value of CH is absolutely unknowable, even with fancy principles that we haven't yet discovered. But still, there is a fact of the matter, even though it may be unknowable, there is a fact about it. That's
which matter?
And what if
Which matter? The fact of the matter, which matter?
Whether this is true or false, that's not the question you're asking.
Is a fact of the matter.
Yeah.
Which matter?
Which matter? There is okay. So this, according to this classical view, there is a reality that makes this true or false. So it's you can talk about all numbers and all sets of numbers and all sets and sets of numbers, and that means something.
So I'm wrong to be thinking about infinite amounts of physical objects.
Sorry, I didn't understand your question.
So I mean, what about, I don't have to have this is just about mathematical objects. There's no physical.
Yeah. It's not. Yeah, this is not saying anything about physical reality. Yeah. Okay.
And you limit that that is reasonable, but to be clear, you continue the continuum hypothesis to zeta 3, so you're not interested in any other set of natural numbers. Equivalent.
So
you do not take the continuum hypothesis as a hypothesis about zeta f, but about a set of natural numbers. You
Right.
limit it. to
Yeah. I'm just thinking about third order arithmetic, which is a small part of ZF. I'm the point is I'm saying that even that small
Yes.
even that small theory, you have to doubt the consistency. So if for URI, you're going to doubt the consistency of ZF. Right. Okay. So now we're ready for probably this is the most
And the
controversial.
natural number that you're speaking about as taken to be defined, the we see that I have as for norm and definition, for example. Or you think that there is something in some way independent of this definition?
Well,
they are
if you would-
given independent.
okay.
So what are the natural numbers you are
If you're in Z3,
as defined in Z3?
Z3, the natural number is a primitive concept, right? It's a third order, it's a three sorted theory, one sort for natural numbers, one sort for sets of natural numbers, and one sort for sets of natural numbers. So it's a natural number in that theory is a primitive concept. But yeah.
So you need much less than ZC for your.
Yeah. But my point is, even with that small amount, you if you're doubting the bivalence of continuum hypothesis, then I'm saying that you should already doubt consistency.
Okay, and then this is really a question that I do not know. Question of knowledge. What is the relation between Z3 and axiom of choice?
Okay, so Z3 does not include the axiom of choice. So I said here, okay, go back. Right, so Z3 is contained in ZF, which does not include choice.
Okay. Good. Okay.
Yeah, so I mean, I think you can add choice to Z3 and that will not affect the consistency. Pretty sure that's right. Okay, likewise, you could add dependent choice to Z2 and it will not affect the consistency. Okay, right, now, okay, now this is probably going to be quite controversial. So these are the principles that everything is going to be based on. So I'm calling these the principles of justified belief. I worry a bit that this phrase justified belief is a bit too moralistic. And it indicates that if you don't follow these beliefs like everybody else in the world, then you're basically indistinguishable from a flat earther, which is probably not what I want to get, the message I want to
Oh,
communicate.
yes, it is.
But anyway, yeah. So,
Well,
so
and
these-
a word that people use sometimes in this context is warranted belief,
warranted belief.
which is a little bit softer than.
Okay, warranted belief. Okay. Well. Okay, so obviously these are open to dispute. No doubt everyone is going to dispute them. But anyway, so let's start with the first one. So I should be clear. When I talk about doubt and skepticism in this talk, I mean an absence of belief in whatever. I don't mean a positive belief that something is false, right? Belief does not commute with negation, right? There's a big difference between not believing in X and believing in non-X. So when I say that certain people who are skeptical about certain things ought to doubt the consistency of this theory, I certainly don't mean that they should actually believe it's inconsistent. I just mean they should not believe that it is consistent. So if you thought you were coming to this talk and hear exciting new arguments for theories to be inconsistent, I'm sorry, that would be a much more exciting talk than the one I'm going to give you, okay? I'm not going to give you any reasons for believing inconsistency, just reasons for not.
In any case, if Z3 is inconsistent, so the continuum hypothesis is probably true. Also, the negation is probably true.
Yeah, if Z3 is inconsistent, then I don't think people would worry about continuum hypothesis.
What of probably
Yeah,
true.
bigger problems.
Yeah.
No, I mean, at that point, we don't have any problems at all. You know? We have inconsistency, there's nothing to worry about.
I'm not sure about that, but anyway, maybe that's a different discussion. Okay. So the first thing I want to do, the first of our principles is that doubt is the default. So I'm going to do this with start with an example, the Cleopatra hypothesis. To say, other people have given other examples of this kind of thing. So there's a statement that over the course of Cleopatra's life, she ate an even number of grapes, right? This is the Cleopatra hypothesis. Now, obviously, there's no evidence for or against this statement. And Now, if somebody believes this, they could be right, but obviously that belief is just arbitrary and unjustified. So the correct position is to doubt this statement, which means, remember, an absence of belief. Because we're not measuring beliefs on a scale from 0 to 1, right? You either believe or you don't. Well, then maybe that's itself a contentious point. Go on.
Yeah, why are from I'm in the statistics department? Why am I not allowed to have a continuum of beliefs?
Okay. Well, okay, maybe doubt. Maybe you feel that doubt should be defined as any belief less than 1.
Okay.
I don't know if that will answer your question. Probably I will say things that contradict that idea, but maybe that will satisfy. I don't know. Like, right. So for the next example, so that's our first principle is that doubt is the default position, right? Every proposition is conceived in doubt. Until we have a reason to believe it, we doubt it. Okay, for the next example, we'll look at the go-back conjecture, which is every even natural number other than 0 and 2 is a sum of 2 primes. This has been checked for a lot of numbers. I asked this person by email, and he told me it's been checked for all numbers up to 4.01 times 10 to the 18 plus 2. Why plus 2? Because when I asked him, I think he checked another one because he didn't want it to be a round number. Okay, I don't know. Whatever. That is what he went up to. That was in 2022. It may check more since then. Not as far as I know. Now, in order to discuss this, obviously, I don't want to bring infinity into the story when I don't have to. So I'm going to introduce this notation, which is nat-g. That means not the set of all natural numbers, but just the googolplex bounded ones. So that's natural numbers less than or equal to googolplex, right? Which obviously is a very big number, bigger than the number of atoms in the observable universe, blah, blah, blah. So a couple of variants of go-back, which will be helpful for our discussion. So googolplex go-back, that says, instead of saying for every natural number, it's just talking about the ones that are googolplex bounded. Of course, this is much bigger than the region that's been checked. And the other one that I quite like is liminal go-back, which is just, this is extreme, right? The smallest thing you can have, the least even number that hasn't yet been checked. So that means 4.01 times 10 to the 18 plus 4 is the sum of 2 primes. Okay, so these are 2 variants of go-back. Okay, so let's talk about googolplex go-back, which is obviously there's no infinity issue.
Sorry, what is exactly googolplex?
Googolplex is 10 to the 10 to the 100. That's the name of that number. So it's a really large number, which is bigger than all the number of atoms in the observable universe, and probably the number of configurations.
Okay.
So we don't know, obviously we don't know whether googolplex go-back is true. So according to the first principle, we have to doubt it. What would cause us to believe it? So now, what I'm going to say, this is my view, the only thing that would cause us to believe it are proof or intuition or a combination of proof and intuition. So typically when you're proving, you have some axioms and rules of inference, and I'm kind of saying that those come from intuition. Whatever that emotion is that leads you to accept it, I'm calling that intuition. Maybe intuition isn't the best word because it's used for a lot of quite different things, but hopefully when we see that, I mean, I can't think of a better word, so there we go. And of course, as soon as we start having intuitions, and we have lots of intuitions, we have to start to make the judgment about which intuitions we're going to accept, because we're not going to accept all of them. Some of them, we know there are plenty of intuitions which lead us into, falsehood. So that's a tricky issue. But what can we do? We can't avoid this problem. So one thing that people raise, of course, is inductive evidence, because we've just seen there's a lot of inductive evidence for googolplex go-back. And there's even more inductive evidence for liminal go-back. I mean, just imagine that. I mean, if liminal go-back is false, so think how ironic that is. It means that this guy, or this team, actually, people, they did all this effort to do a big experiment, and they had to stop somewhere, of course. And where did they stop? Just before the least counterexample. I mean, that would be, it could be the case, but, so that's probably the most inductively evidenced statement you can come up with. And by the way, I'm understating the inductive evidence here because there's all kinds of other ways of arguing this, but anyhow.
But this happened before, right, with the Fermat numbers?
Pardon?
This happened before with Fermat prime numbers.
What happened?
There was the hypothesis that Fermat numbers would have are prime, and they checked several of them, and all of them were prime, but the next one was not.
Okay, right, okay, but they didn't check 4.01 times 10 to the 18.
It wasn't that big, no,
Okay.
but still the Fermat
Right,
numbers are
okay.
quite big.
Okay, so that's a good argument. That's going in the direction that I like. So inductive evidence, however strong, is not adequate grounds for belief, right? Because I've said only proof and intuition. And now I've said that this sounds like an appeal to authority, doesn't it? Mathematicians throughout the ages have largely agreed that this inductive evidence is not something we can rely on. Okay, this is inductive evidence reject.
This is true. It's not evidence for proof. It's not good for proof. But the history of mathematics is full of examples in which inductive evidence is strong enough for conjecture that are conjecture on which a lot of mathematicians work. Case of Fermat, Goldbach. Why we believe, not in your sense, but why for 2 centuries mathematicians try to prove the Goldbach conjecture. Because in some sense, they believe that it's true, and in which sense they believe that it's true because they have no example. So you are not, of course, I use in believing in another sense that you don't agree with anything that you said.
Yeah.
But I don't know. It seemed to me that
So you could say there's different kinds of belief.
there is different kind of belief. There is at least a kind of belief in which what you say is wrong, historically wrong.
Okay. Do you have your hand up?
Yeah, you seem to be ruling out this kind of inductive evidence as a source of intuition.
Yeah, because I was thinking of the example of like P versus NP, right? And so is that a case of, yeah, is that a case of inductive evidence or a case of intuition?
Okay, well, actually, okay. So I mentioned P versus NP on the next slide, as you can see. So this is okay. I mean, I got criticized for my negative statements about inductive evidence before, after the paper came. So, so of course, it is true that inductive evidence is taken seriously. So, for example, in number theory, it's a Goldbach conjecture. In complexity theory, there's this thing called an invisible fence, which people appeal to as a justification for why they believe P not equal to NP. I don't know if that's intuition, though. It's not. I mean, I don't know if you meant like just the idea that it would be really strange to be able to that being able to verify something quickly means that we can find it quickly. Invisible fence is more like an inductive. We found a lot of cases that behave in the way that you would expect if P were not equal to NP. They classify various problems and they all form on opposite sides of this fence, which kind of suggests that there's something going on here that we can't prove, but we think is there. And even more, and even I wouldn't say that's a case of inductive evidence leading to intuition, though. I think
yeah, no, so I was thinking of the just like, oh, it would be very strange if everything that could be polynomial and verified could also be proved. So this is helpful to think about what the inductive evidence is in that case.
But you are taking inductive evidence to be a different thing than intuition, or rather, intuition is a different thing than.
Yes, very different.
Okay.
I can't think of any case where the one goes with the other, to be honest.
Well, I'm looking for your definition of intuition.
Okay, I'm defining it.
Well, I know, but you are at least ruling out. You're not. You're saying that that's not part of what you mean.
Yeah.
Oh, that's fine.
I mean, of course. I can think in the past year of at least 2 cases where I really used inductive evidence to guide me, and then it was really helpful. And I'm sure that's true for everyone who, every mathematician. So, and here's another example. This one is probably bigger. In set theory, people have used inductive evidence to support hypotheses like ADLR, and the phrase they use is extrinsic justifications. They say, we've got a bunch of phenomena that are nicely accounted for by this hypothesis. And they may object to having this even compared to this experiment with the Goldbach conjecture, because this is much more sophisticated than just running a computer program that checks a bunch of examples, right?
Sorry, 2 things. First, so you think that inductive evidence is not a ground for belief, but you say that inductive evidence is a ground for support, for support.
Yeah, I use the word
Supporting is
support.
something different than belief.
Yeah. Well,
I
I,
do not see very well the difference.
okay, but it for
And the second point,
Go on.
I do not know the discussion about ADLR, but if I understand well, it is more than inductive evidence, is belief in the better explanation. The fact is the better hypothesis to account from this evidence.
okay, so
Inference to the better explanation is not more than
is it more than?
That
Because
is
I think
evidence.
from my point of view, okay, this may go off in a different direction, but I mean, I guess I'm using inductive evidence quite broadly here.
Okay.
But I looked at some of the writing about extrinsic justification for this hypothesis, and a lot of it is like, well, we have some different phenomena, and they're brought together by this hypothesis, which explains them all which explains or predicts, more accurately, predicts them all very nicely, and that's then, so these are data points that corroborate that hypothesis. So to me, that sounds like a kind of inductive evidence. So I mean, I'm not saying that all inductive evidence is of the same kind, and there are different kinds of inductive evidence, but I do think that there's something in common between these different kinds of arguments. And anyway, now this statement doesn't really justify anything, but this is not the kind of evidence that I'm relying on in this talk. I mean, I'm going back to this traditional view. You can only believe something as conclusively once you've via proof and intuition, and not via inductive evidence. So I'm really separating that.
So is your belief as strong as knowledge?
I think so, yeah. I think, yeah, I would use the word knowledge as well as belief. Maybe people might use belief for something weaker,
Yeah.
and knowledge for something stronger.
Usually knowledge is belief with justification and yeah, something else.
Knowledge is justification.
True
Justification.
Justified belief.
Well, yeah, I mean, okay, so there is that definition of knowledge, but I don't know how well it fits in this mathematical setting. I mean,
Yeah.
Yeah. I'm not sure I can say much more about this, to be honest. I mean, I tried to at least mention that there are very many kinds of inductive evidence, and they're certainly not ignored, and they are used as support. But I mean, the rest of the talk, it was almost like the basis of the whole talk is that we're refusing to accept any kind of inductive evidence. It could be, I mean, there are a lot of things you could say about this. I mean, I could go off a whole direction. You could say, why should inductive evidence be unacceptable in maths and yet it's acceptable in other sciences? If it's acceptable in what, or you could say, is it the case that maybe just maths attracts people who hate relying on inductive evidence? Maybe that's what attracted me. Don't have to worry about all that statistical stuff. But yeah, so there are definitely questions you can ask here.
I've from time to time wondered if that was not almost a definitional thing. Like, what is a mathematician? It's
Somebody who
this
doesn't
person
accept
is not going to accept inductive.
Yeah, it could be. But yeah. Anyway, so but the basis of this is not accepting inductive, and you're going to see in the next very soon, why this is so important. So let's talk about consistency statements now. So we say we've got a theory. So I'm going to write con T is the assertion that T is consistent theory, which means that false is unprovable, right? Con G, well, of course, like I said, I prefer to avoid infinities if I can. So especially for this talk. So con G of T says that it's googolplex consistent. That means no proof whose length is googolplex bounded, right? So that avoids the quantification over the natural numbers. In order for this to make sense, we obviously have to very precisely define proof length. And we can easily do that, right? For all of our theories, you can cook up a precise definition of proof length. So I'm assuming that's being done. Okay, so those are the consistency statements that are going to come up in the talk. So consistency statements are not fundamentally different from statements about prime numbers, right? They're statements, combinatorial statements of a certain kind. So, for example, this one is the Googleplex consistency of third order arithmetic. Following the rules that we've set out, our default position is to doubt it, because like same for any set statement. The only thing that will give us the adequate grounds to believe it are proof, intuition, or a combination of those. That's it. Now, yeah. And by the way, of course, we have theorems like Gödel's second incompleteness theorem saying that under certain cases, in certain situations, we can't prove consistency. But they are not a ground for relaxing our standard. I mean, the standard is what it is. And if we are doomed to ignorance, then we are doomed to ignorance. And we just have to accept that. So that's okay. Now, I hear this argument. This is called the clever people argument for consistency. So people, and I've heard this quite a few times. I've seen it in books, and it's this actually discussed quite a lot by Pazzo, has in a paper on inductive argument. So people say, many clever people who've used this theory for years and years and studied it in detail, and they've discovered no contradiction. And it's quite, again, I mean, we are wired to accept inductive evidence. So this does seem, when you're thinking of ZFC, you think nobody's going to find an inconsistency. I mean, you'll think of all these, it would have happened already. This is what you think. But this is an inductive argument. So the principle we follow, this we cannot accept, right? Inductive evidence for consistency is not going to be acceptable because I said we're not accepting any kind of inductive evidence, right? So only proof and intuition. It's the only argument for consistency that we're going to accept.
So what you would be of this following argument for the consistency of piano arithmetic? We have a constructive definition, not axiomatic, of natural number as the closure under the progression, under the addition one. And so using this abstraction definition, we construct a model of piano. So here's a model, so it is consistent.
So that would be, okay, depending on how you say it, and depending on the, and we'll say more about this argument later. I mean, that's either, it can be an actual formal proof in ZF, for example, although that's probably, if you're doubtful about the consistency of piano arithmetic, you're probably not going to care very much about what you can prove in ZF. Or you can see it as more kind of informal argument. But we'll talk about that later. Maybe that will be better. But at the moment, I just want to say that we've set a standard of proof and intuition. We're not accepting inductive evidence, and that's our standard. So, okay, and yeah, and here was a nice comment by Joe Hankins, who said, against the clever people argument, he said, the negation of Fermat's last theorem turned out to be inconsistent, even though before that, many clever people had looked seriously and hadn't been able to refute it. So, he's saying that the clever people argument sometimes don't work. Okay, but even if it had worked on every previous occasion, of course, that wouldn't be good enough, but it hasn't. Okay, so here's a summary of our principles of justified belief. So for any statement, we start off by doubting it. If we have no reason to believe it, then we doubt it. The only thing that will move us from our default position of doubt into a position of belief is a combination of proof and intuition. Now, as I said, intuition is a tricky matter. We're going to have to make tough decisions about which intuitions we're going to accept. And we are not accepting inductive evidence. And all of these principles apply to consistency statements. We don't treat them any differently from any other kind of statement. Those are the principles that everything that comes afterwards is based on. Okay, so no inductive evidence. Right, so that's the end of part 2. So you can have a bit of a break.
Yes, I'm making you notice that you are taking 45 minutes.
Do you know?
And the other one.
No, it's like all right, this is slow.
The breaks are not.
Yeah, but this is slower than I thought. Well, I said 2 minutes. So I think
Well, because we do interrupt. This is what
Yeah.
this is what we do.
well, that's good.
Yeah.
I mean,
Yeah.
mm.
These things out.
But if they're linked to me,
It will be, it might be, we might end up on a cliffhanger if we only get, yeah.
E over.
Mm.
I'm going to make my own.
It's only inductive evidence that we're going. slowly. Going slowly so far, though, is only inductive evidence.
Yeah.
Doesn't mean the rest of the
That's
talk
true,
will
that's
go-
true. Actually,
Yeah.
probably the most, it could be the most controversial part of the whole.
But I have an intuition that it'll all go.
That will continue to interrupt.
Because that they're going to hire us 10 coins in his pocket. But then the decision of the committee is overruled by someone who just want to hire someone for by nepotism. It so happens that the person has 10 coins. It's good that, I mean, he was justified in believing that the guy was. And it was true. And right. A true belief and justified. Right. Did he know?
Yeah, there was no nice.
You think I should carry on, or I think I should wait a minute?
Yes.
Okay, right. Okay, so now we're ready to we're ready for the bivalence questionnaire. So this is actually, I think, my favorite part of the talk, which even if you disagree with everything else, hopefully you will at least like this. Going to go through a list of open problems, and this is going to help us think about our intuitions and beliefs. And all of these are, the truth value is unknown, and I use the math overflow community to help me compile it. So to begin with, we have, and they're different kinds. I'll classify them. So we'll start with two very special examples. So physical sentence about the physical world, the Cleopatra hypothesis, right? And a computational sentence. You can think of this about a computation that could in principle be done. Googleplex Goldbach, right? And note the form. That's saying for all n bounded by Googleplex, a certain property holds. Right. These are the first two. The rest of the sentences I'm going to present are in pairs. So the first example will always be a single quantifier, and the second example will be a double quantifier, right? Just, I mean, just to, well, there are reasons why I want to do this. Let's start with arithmetical sentences. So this means that the quantifiers only range over natural numbers, right? So we have the Goldbach conjecture. Now, I've written out the conjecture, but actually this stuff, the actual statement is irrelevant. What I really want you to look at is the logical form in red, right? Every natural number has a particular property, and that property is computation. And the technical name for these sentences is pi01, or you could just call them falsifiable, right? Because if this is false, there's a counterexample, but so they're falsifiable in a certain sense. The twin prime conjecture is a two quantifier version. For all n, there exists n, right? Technically, it's called pi02. Okay, that's arithmetical. We move on to second order arithmetical.
Sorry.
Yeah.
It is true that this, but Goldbach conjecture wouldn't be for all n. There exist p and p1 and p2, so that.
Yeah, but this is phi n is computational. So if you're given a natural number, checking those two primes are going to be bounded by n.
N.
So
I see.
once you've got the n, you can just do a computation and get the answer. It might be very long, but
Well, in the second case, it's not the case.
right.
Right.
Yeah, these are
Because you
unbounded.
know how long you have to take.
So this is not falsifiable in that sense. Okay, so second order, I could say ranges over sets of natural numbers. I prefer to say range over bit streams. Okay, so Littlewood conjecture, ignore the statement itself. I'd never heard of it before, but anyway, as I say, all we care about is the logical form. For every bit stream, blah, blah, blah. And the stuff after the quantifier is all arithmetical, right? So that's pi11. And the Toeplitz conjecture, every closed curve contains 4 bits equal to a square. For all bit streams, there exists a bit stream such that something arithmetical.
Arithmetical means
Means that all the quantifiers range over natural numbers.
all the quantifiers. Okay.
Right, so arithmetical means quantifiers range over natural numbers. Second order arithmetical means quantifiers range over bit streams.
Predicative. Predicative. Sometimes it's a predicative.
I
There
haven't.
are no second order quantifiers.
Well, okay, the word predicative is used in several ways. Okay, I prefer, okay, I prefer to call it arithmetical, but.
Okay,
but-
okay.
It is definitely connected to issues of predicativity, I agree with that. Right. Third order arithmetical sentences, they range over functions from bit streams to 2. Again, I could say sets of bit streams. I prefer to do it like this. It maybe become very wide. So the continuum hypothesis says there is a function from bit streams to 2 such that some property that is second order arithmetical. It's not actually completely obvious. Sometimes you have to do some work to put sentences into a certain logical form. But this is a sigma to 1 sentence because it's got this form. And the Suslin hypothesis, it's for all functions from bit streams to 2, there exists a function from bit stream to 2. And everything after that is second order arithmetical. When with the point you see here, when we're thinking about third order arithmetical, we only care about these quantifiers, and the ones that range over 2 and that, they don't matter anymore. They're considered trivial. So that would be called pi 2, 2. Okay, now you might expect me to carry on to fourth order. I'm not going to do that. I'm going to jump to unrestricted set theoretic sentences. This time, the quantifiers are going to range over all ordinals. If you're not familiar with ordinals, don't worry, it's not the main part of this talk, okay? This time we have generalized continuum hypothesis. The form of this is for every ordinal phi of alpha. Oh, that should be kappa, I suppose. That's a bit much. I knew there would be a typo. I never talk about typo. Okay, phi of kappa. So phi is restricted. That means that all the quantifiers in phi are ranging over a set, not over a proper class. This one is ranging over all the ordinals, but the quantifiers in here are ranging over a set. And in constructing the set, we're allowed to use power set. So it's not just in the language of the usual language of ZF, which doesn't have this as a primitive symbol. Okay, eventually generalized. Some of these examples, by the way, are contrived especially for the sake of this talk. This is one of them. So this says there exists an ordinal such that every ordinal blah blah blah, right? And what's inside is restricted. So those are the unrestricted sentences ranging over all ordinals. And now we're going to go even wilder and go to class theoretic sentences where the quantifiers range over long bit streams. So they're not like omega sequence of bit streams, but an odd sequence of bit streams, very, very long, right? Proper class long. So here are 2. This is another one that's been cooked up. Oh, you can't see that's in blue on blue. Sorry, Schlutzenberg. The club failure hypothesis says for every long bit stream, blah, blah, blah. And this inner thing is all set theoretic, right? So it's allowed to quantify over all the ordinals, but none of these fancy quantifiers. And the Ord-Suslin hypothesis, Hampkins and Switzer, has this form. For all long bit streams, there exists a long bit stream such that something is set theoretic. Okay, this is the end of our questionnaire. I could go up even higher to, functions from 2 Ord to 2, but I'm going to stop there, and maybe you think I should have stopped some time ago, right?
So in order to write this formally,
Yeah.
you will need a language in which you can speak about class,
Right. These are not
function-wise.
expressible in the language of ZF.
but maybe in the NVG or.
Yeah, in a class theoretic language, that's why it says class theoretic, you would be able to express that. Yeah. Okay, so now let's think about what are the prospects for solving these problems. So I'm going to give you an optimistic scenario and a pessimistic scenario. Right, the optimistic scenario.
Problem to know what the 2 are pessimistic.
Okay, the optimism in the sense that we learn, get a lot of knowledge, and pessimism in the sense that everything is unknowable. That's why. I mean, you might that's what I'm considering. So the optimistic scenario is that first of all, we'll come up with new archaeological techniques to solve the old mystery of Cleopatra's diet, right? And resolve, I mean, either prove or refute. And then all the first 5 sentences, not Cleopatra, but the other next 5 sentences before continuum hypothesis, they're all going to be resolved in ZFC, maybe even in a weaker theory. And as for continuum hypothesis and the rest, well, they're not going to be resolved in ZFC, but we're going to come up with new, obviously true principles that will resolve them. That's the optimistic scenario, all right? Okay, much more relevant for this talk is the pessimistic scenario. So this basically says that all the sentences in the questionnaire are absolutely unknowable. So this says Cleopatra can't be resolved in any way. By in any way, I mean even using other techniques that we haven't yet invented, right? We have to be a little bit careful with googolplex go back because some things we have to say within the lifetime of the universe, right? Because obviously I couldn't say that it can't be resolved in any way with a sufficient amount of time, but this is as pessimistic as we can go for googolplex go back. For go back, I also don't want to say it cannot be refuted because that would imply that it's true, right? Because if it can be refuted, if it's false, it can be refuted. And also, I'm not just saying that we can't know them, but we can't even reduce them to something simpler. So Littlewood, remember, was second order arithmetical. I'm assuming that we can't reduce that. The pessimistic scenario is that we can't even not only can we not prove it or refute it, we can't even reduce it to the next level down to arithmetical. And for the sentence, which is for all exists, we can't flip the quantifiers. So this is the maximum pessimism about what we can know. Right? So this is only a rough summary. This pessimistic scenario means all of these sentences are absolutely unknowable. Right. That's all set up for the questionnaire. Okay, so now it's your opportunity to participate in this process of discovery. So what I want you to do is assume the pessimistic scenario, or at least bear in mind that it could be that these sentences are all absolutely unknowable. So the question is, which ones do you think are bivalent? This is absolutely the crucial question that, in everything goes from this. So it's about looking inside to your own intuitions and emotions to try to think what is bivalent, which of these sentences are bivalent. So that means to spell it out one at a time. So do you think that even though we are hopelessly ignorant, because we're assuming we're being pessimistic, right? But do we think that there is a fact of the matter that either she had an even number of grapes or an odd number of grapes? I know at this point people are going to start asking, what about partial grapes and fruit salads and all of this kind of thing, which is really going off topic. But anyway, do you think there's a fact of the matter whether every even googolplex bounded number, this is googolplex go back, right, other than 0 and 2 is a sum of 2 primes? Do you think it's a matter of objective fact? I can't answer these questions for you. I mean, I'm gonna argue against certain combinations of answers, but basically, I'm happy for you to say no to everything, and I'm pretty happy for you to say yes to everything. Let me make when you go through this, right? Here are some notes, some guidance notes to think about. Because really, to me, I want, if I'm going to talk to somebody about, their view on foundations of maths, I want them to do this questionnaire so I kind of know where they're coming from. So if you answer yes to a question, that means you think it is bivalent. It's either objectively true or objectively false. If you answer no, that means you doubt the bivalence. That means you have an absence of belief. It does not mean you think the sentence isn't bivalent, right? I'm not asking, that's not a question. Also, so leaving aside Cleopatra, the questionnaire goes in an increasing order of logical complexity, right? It's designed in that way. So if you answer no at a particular point in the questionnaire, there's not really any point in carrying on because obviously the rest will just look increasingly incomprehensible to you, right? So generally, if you're a kind of person who is skeptical about reality, who doesn't think there's mathematical reality, that kind of thing, probably best to focus on the first few questions, like googolplex go back. If you're a kind of gung-ho Platonist, better to focus on the last few, right? So focus on the bit which is kind of relevant for you. But so that is my I think that's the right. Oh, this is another important point, right? Bivalence, ambivalence is allowed, and it's even encouraged. So what do I mean by this? So we tend to assume, like in philosophy, you assume that each person has their own point of view and they're not ambivalent at all. So right, but that's obviously an idealization. So it's fine to say, well, like this section, I'm like mostly certain that this is right, but there's another section of my mind which is a bit more skeptical, and another section of my mind which is a bit more credulous. I'm happy to have different sections of your brain that think different things. That's fine. Okay. So that's what I call ambivalence, right? That's allowed. And I encourage it because if if that's why you find yourself, and that means you're engaging with this question, you see that there's something difficult here, right? Instead of just trying to wave it out and say the answer is obviously these questions are, the answer is obviously yes or obviously, you see that there's a problem here. And I hope that because of this wide range of sentences, that I do hope that most people will at least say yes to the start, to Googleplex go back, and perhaps say no to those class theoretic sentences at the end. So at least they get some sense of what it is to be prejudiced and what it is to be skeptical. Right. And okay, that's the end of section 3. So I don't know what kind of gap I should be now. I think this 2-minute thing is now being thrown in the bin, but I'm going to leave a few seconds at least, right?
But
Yeah, are you going to put the questions?
So the questions are for each. Okay, I can go back, right?
Yeah,
So,
I don't remember all.
yeah.
the
Right, let's go through it again then, quickly, but quickly this time. Right, so each time you want to know, is it bivalent? Is it objectively true or objectively false? So is it a matter of objective fact whether Cleopatra ate an even number of grapes? Is it a matter of objective fact whether every even Googleplex bounded number, this is a bounded number, is a sum of 2 primes?
sorry.
Yeah.
My intuition here is that both are equivalent, and overall all what about the Googleplex ambivalent, but for a reason that perhaps you would be surprised of, because I believe that it's perfectly possible that very powerful computer will invent tomorrow, and that will go so quick that during my time life they can be able to verify all the number as to Googleplex. So this is a belief not in mathematics but in technology that make it believe that they are equivalent. If you eliminate the Googleplex and you consider infinite versions,
Which is the next
so
question.
I think that they are not equivalent.
Okay, so you're doubtful.
No, but Marco, you're appealing to what might be knowable, and that's not the same question.
Of course, I don't think what does it mean. Equivalence.
No, that it has a factor. There's a fact of the matter. Is the question of bivalence, not
I think
not
that is a fact of the-
knowability. So your appeal to technology, I don't understand.
Well, the
Because
thing.
I do not understand what does it mean, the fact of the matter, independent of the fact that the proof is probable.
Okay, so you're skeptical about the bivalence of Goldbach conjecture,
As such,
but
yes.
you believe that Googleplex Goldbach is bivalent because of a possibility of technology. Now, I've chosen Googleplex here in the hope that it's big enough to make that idea that technology could solve this problem like impossible, although I do realize that that's dependent on certain physical assumptions that are open to debate, right? This, as I say, it's bigger than the expected duration of the universe, blah, blah, blah. It's deliberately.
In this case, I'll be skeptical also about.
Okay.
When in the next one, the Goldbach conjecture, when you mean true, do you mean that it is provable in piano arithmetic, or
No,
that it is
no.
true in the standard model of the natural numbers?
Yeah, the latter. I have to say, by the way, I find it quite amusing. I say this to a lot of people. What you said is what many people say, to refer to the set of all natural numbers as the standard model of like piano arithmetic, like bringing in a theory and the notion of model to say something which is just a set of all natural numbers. That always makes me laugh. But sorry, I shouldn't have said that. I'm not going to say a lot of people do
Happy
this.
to make you happy.
Okay. Anyway, yes,
Are you
that's what I
sure
mean.
that there is a
There's
difference
true in
between the two?
Of course.
But that's like, it's
How can you
because I always want to bring in a, it's because I always want to bring in a model and a theory that I think, like, that's why I'm gonna be, why I'm gonna say no, right, on the basis of
Okay.
this.
So you want to say no to go back?
So I'm not sure about gold.
Googleplex go back?
We can prove, for
You okay with
example,
that?
in the
Yeah, I guess I'm okay with Googleplex.
Okay. Right.
every Kochstein sequence is going to be eventually 0, but we cannot prove it in piano arithmetic.
Okay, but this is definitely not a question about
Okay,
piano
okay,
arithmetic.
proven in the theory. Okay.
Just
You just made a theory.
just to make this clear, specifically said, assume the pessimistic scenario. So that's assuming that these things, that Goldbach cannot be proved in ZFC or in any way at all. That's our pessimistic scenario. And I can't assume that it can't be refuted because that would make it false necessarily. But at least in the lifetime of the universe, there's no way of breaking it down to a computation. So it's definitely not a question about any. These questions have nothing to do with any formal theory. They're not. That's not what they're asking. I mean, I don't mean they're not related, but I'm not asking about any formal theory. I'm just asking whether you think there is a fact of the matter. If, as I say, once you hit no for a particular question, if you hit no with one part of your mind, but you think, well, I think no, but I can understand why somebody might think yes. That means there's like a little part of your mind that thinks yes. Then you can carry on for that part of your mind going to the next question, right? But if you think, no, this is completely ridiculous, there's no point in carrying on to the next question.
Okay. What comes after Goldbach?
Okay, sorry, let's go back. Right. Okay, so after Goldbach, we had twin prime, which again is for all natural numbers, there exists a natural. So it's 2 quantifiers instead of 1. And then it's quantifiers ranging over all bit streams. So not ranging over natural numbers now, but ranging over all bit streams. And again, we have 1 quantifier example and a 2 quantifier example. And then the next one is functions from bit streams to 2. And we have a 1 quantifier example and the 2 quantifier examples. It's getting more advanced. Then we have sentences with quantifiers ranging over all ordinals. And we have a 1 quantifier example and a 2 quantifier example. And lastly, quantifiers ranging all of these long bit streams, and there are a lot of them, right? Even by, even bigger than the board, right? And again, we have a 1 quantifier example and a 2 quantifier example. So that's the summary, right? So it's really ranging, and each case is asking, do you think there's a fact of the matter? Until the point when you say no, and that's kind of the end, right? So, and I'm definitely not saying, because I'm being pluralist today, right? So I'm not saying what's right and what's wrong. I will say some things about that, but only very little. Okay, we ready to move to the next section. Okay, so I now want to talk about schools and intuitions, right? So that's the next sentence. Okay, so I mean, these questionnaires, not so elaborate as this one, but small versions have appeared before. I've seen at least 2 examples. And I see them as the kind of, they are crude, and I recognize that, but they're kind of useful way as a kind of diagnostic tool for measuring somebody's belief in some kind of objective reality. That's kind of, and that belief, I'm going to use the words interchangeably. You might disagree with that, but I'm going to use realism and Platonism interchangeably. And that, I'm going to say, it means belief in objective reality. I will talk a bit more later about what does it mean to believe in reality, and believe in mathematical reality. But the point of the questionnaire is to measure your belief in objective reality. So I'm going to give some names to different positions. So Marco said that he doubts the bivalence of Google Pets Goldbach. The name I'm going to give is ultra-finitist, right, to that position, which many people have espoused. The finitist is happy with the computational sentence, like Google Plex Goldbach, but draws the line at Goldbach, does not believe that Google, again, remember, it only means an absence of belief, nothing, no positive belief. Does not believe that that Goldbach is bivalent. That's the finitist. The countabilist is fine with quantifiers that range over NAT. Right, and this is somebody like Weil, for example. You mentioned predicativism, right? He's happy with those kind of sentences being bivalent. But when it comes to ranging over all bit streams, he has a problem. And there are many people who've adopted this position. The sequentialist is the next level up. So they're okay with sentences ranging over bit streams, but not with ones ranging over functions on bit streams. And also the sequentialist, and I'm joining these things together, and you'll see why, believes that independent choice. And then we come to the particularist, who believes in the bivalence of the third order sentences and higher, and they're not being very precise, but they certainly do accept the third order ones, such as Continuum Hypothesis and Suslin. And they also accept the axiom of choice. But when it comes to the sentences that quantify a range over all ordinals, there they have a problem. So this is me, by the way, I'm particularist. Right, this is my position, but that's just my position. It will hopefully give you a bit more later about why, but still, I'm not telling you that's what you should think. The totalist goes further and is happy with quantifying over all the ordinals, but is not happy with quantifying over all long bit streams. They draw the line there, right? And as for views that are even more credulous than this, that are happy with those quantifiers over the all long bit streams, I'm not going to consider those in this talk. I'm not saying that they're bad or anything. I'm just not going to consider them. Okay. Other people do essentially consider such views.
There is something that's called Platonism like this. Platonism would be one of them.
I
you
would
not consider
say
Platonism
that
as-
other than the ultra finitists, well, I'll come to this, that all these views are Platonist, but to different points. So we'll come to that. So here's some questions. Go on, yeah.
When you say, for example, third order arithmetical, you mean all of them? Because someone could say that I believe some third order arithmetical sequences are bivalent, but maybe some others are not bivalent.
Okay, I think no, I'm not going to say. Oh, sorry. For what they do believe, I'm going to say yes, but for what they doubt, I'm going to say no. So, I mean, a finitist might say that they accept that certain arithmetical sentences are bivalent, but I've deliberately given examples for this questionnaire. So let's just say the ones in our questionnaire. That's good enough.
Yeah, but then
This is
here
not
you
really a
mentioned the axiom
definition.
of choice, but then in the questionnaire, the question was about the continuous hypothesis.
Yeah. So okay. These are not. I should say these are not definitions. Maybe I'm not okay. I'm going to try to explain what these schools are really about later. But these are just properties of these schools. I'm telling you properties of these schools, and the sentence I'm really referring to are just the ones in the questionnaire. And I don't want to say all because there are obviously sentences which are special for one reason or another. The sentences in the questionnaire are kind of chosen not to be special. Okay. Although you might. So here are some questions. I've given I've drawn these boundaries. So you could say, is is it just an arbitrary choice between colored pills? In case you said this to me, you take the red pill and blue pill. I can't remember what pill the color it was. Anyway, why haven't? And also, we say, well, why am I giving you so few options? Why not have an option for the person who accepts 17th order and rejects 18th order, or for the person who accepts 52 quantifiers but not 53? Right? Why not? Okay. Well, first of all, so I think my answers to these questions. First of all, I'm going to say belief should not be arbitrary. I mean, I said this long ago, right? And these things seem rather arbitrary that I was suggesting. And also, according to what I've said, that's the word, it should be justified. Belief should be justified by proof and intuition. So somehow, these beliefs that we were talking about, that these things are bivalent, should come from some kind, well, proof is not really relevant here, but they should come from intuition. So that means, and this is I don't, according to this idea that proofs have to, beliefs have to be justified, we can't just be what is usually called truth value realist. Truth value realist is the idea that you just accept. I mean, this could be a caricature, so not everybody who would describe themselves this way would accept this formulation, but just that you don't believe in reality, but you just believe that sentences have truth values. Like they don't come out of anywhere. They just have truth values for no reason. So I'm saying that can't be. We have to have some kind of intuition, and I feel so in a way I can understand the many different positions on this spectrum. I'm not going to say all of them, but I can understand many of these. So there is a part of me that relates to each of these, and those parts, in each case, the belief that, for example, arithmetical sentences are bivalent, it comes out of an intuition. It's not just the belief that that sentence has a truth value. So what I wanted to kind of take a look at what are these intuitions that are leading a section of my brain and perhaps your brain to think that these sentences are bivalent. So what I'm going to do is I'm going to present 5 intuitions that, oh no, we're still in section 4, that's okay. Right, we're going to present 5 intuitions that I experience, and hopefully you do too. What can I say if you don't? Sorry. So each of them is a little person inside our head. This is not what you're supposed to say in a philosophy talk, I know. And each of them is going to speak. And all I want for the moment is just this. I'm trying to articulate this emotion, right? That is driving, that this part of my brain that thinks these statements are reliable. So just listen to them. And later we can discuss whether these are reliable, whether they should be accepted, because they're speaking to us, but we don't need to accept what they're saying to us, right? So what are these sentences? So I'll call the first one Googleplex. It's a bit special perhaps, but anyway, never mind. So what does this person say inside our brain? It says, I perceive the notion of a Googleplex bounded number. And this is really clearly defined. And because it's so clearly defined, quantification over this set yields an objective truth value. This is a strong feeling. And then we have, seems to me, a slightly weaker feeling, which is the arbitrary natural number intuition. And what does this say? It says, I perceive the notion of natural number given by 0 and successor. And this is a clearly defined notion. It's as restrictive as possible. There's nothing else, just 0 and successor, just that process of generation. Nothing else is admitted. And therefore, because it's so clear, quantification over this set yields an objective truth value. That's what this natural number intuition is saying. And then we get a weaker intuition, and that is arbitrary sequence. And what does this person say to me? It says, they say, well, given a set B, I perceive the notion of a sequence. And what is a sequence? It consists of these successive arbitrary choices. And it's clearly defined, and it's, I have to emphasize this, as liberal as possible. They're completely arbitrary, the choices, right? And because it's so clear, because it's as liberal as possible, the extreme of all possible notions of sequence, that means that's what makes quantification over this set give us an objective truth value. And the intuition carries on speaking. It says, since that's what a sequence is, successive arbitrary choices, dependent choice is going to hold. And to me, and again, this is just describing my intuition. Other people have said the same thing. Like I say, pretty much everything I say has been said before. That it's the same intuition of arbitrary sequence that is telling me that dependent choice is true. It's not like a separate intuition. It's the same intuition. It's quite an important point. And then we have arbitrary function. This is a slightly weaker intuition, saying that given sets A and B, I have this intuition of a notion of a function. And what is a function? It consists of all of completely independent arbitrary choices. One for each. So it consists of choices. And the intuition says it's a clearly defined notion. It's absolutely as liberal as possible. There's no more liberal notion of function than this. And because it's so clear, quantification over the set of all functions is going to give us an objective truth value. And then it carries on speaking and says to me, since we've said that a function consists of all of these independent arbitrary choices, the axiom of choice holds. It's all one intuition. And then we have the last thing. So we've had 4 intuitions, right? We've had Googleplex and natural number. We've had sequence and function. The last intuition is arbitrary ordinal. And this person says to me, I perceive the notion of an ordinal. And this is clearly defined notion. It's as liberal as possible for this notion to be. And because it's clear, quantification over all ordinals is going to give us an objective truth value. And this is the weakest intuition of the 5, right? I'm going to discuss the intuitions later, but at the moment, we're not criticizing or judging them, we're just listening to them. Okay? So the real, if you like, definition of these schools is not whether they accept the twin prime conjecture or whatever. The real definition is which intuitions do they accept from this list. So the ultra-finitist school doesn't accept any of the intuitions, not even Googleplex. The finitist accepts Googleplex, and the counterbalist accepts everything up to natural number, sequentialist up to sequence, particularist up to function, totalism accepts this last intuition of arbitrary ordinals. So that's really what's driving the division between the schools. So what I said before, this wasn't the definition. As I said, this wasn't the definition of the schools. This was just some properties, but really the definition is this, which intuitions they accept. And like I say, I'm a particularist, but I do understand I can relate to some extent other positions. And I should say, this is a crude taxonomy. And I mean, the most famous distinction, which is not listed here, is between finitists and constructivists. Constructivists accept higher order constructions, and then from this taxonomy sort of lumps them together. But this is, yeah, it was a crude taxonomy. Oh, one other thing on this question of schools, right? You will find some authors who have like Cars he describes himself as a positivist, and he says that Google, go back conjecture is bivalent because it's pi 0, 1, because it can be falsified. But twin prime, no, he draws the line at twin prime. Now, according to the line of thinking that I've been setting out, that's not allowed. So I said I will accept anything, but this is not something I'm going to allow. Right? If you're happy with one quantifier, I'm going to insist you're happy with two quantifiers. Why? Because if this is how it seems to me. If you think that twin prime is, if you doubt the bivalence of twin prime, then you're basically saying arbitrary natural number is an unreliable intuition. And if that's what you think, then I would say even the bivalence of the go-back conjecture is doubtful. Right? I mean, I don't see why you would treat nested quantifiers differently. But as I say, there are people who've done that, and particularly Cars. And it goes the same for all of these pairs. I've given you pairs, remember, single and double quantifiers, and I'm saying you should treat them the same. I don't really. I don't really think you should treat them differently. Okay, right. So that is the end of section 4, and I got like a big break shown here. But
a big break, it could be a break of 1 year. You come back next year to give the other part of the talk.
Well,
Or give the second talk.
yeah. Well, we'll have I think I should definitely have a couple of minutes there at least. Yeah. Oh, everyone wants to ask on there.
I don't know if this is a fair question or not, but when I think about human intuition, I think of that as possibly being grounded in induction, because that's just how human brains work. Is that like how should I think about that?
Okay, so I think we had a similar question from Drew. I'm thinking of intuition and inductive as being very different things. I don't really understand this idea that intuition could come from induction. I mean, maybe, as I say, intuition does mean different things. And sometimes, we're doing research, we have a hunch that a particular statement is true. And sometimes that hunch turns out to be right. And we have got experience, I suppose. Sometimes the hunch turns out to be wrong. I feel that these intuitions that I'm talking about here are a bit different. I don't know what kind of inductive evidence would lead us to those intuitions.
Well, let me ask a slightly different question then, which is that my intuitions seem unreliable, right? I might believe, parallel lines never intersect, and then you show me, actually, in this case, it does whatever, right? You've completely blown up my intuition, right?
Yeah.
How should I think about that if I want to avoid being the sophomore skeptic who gets off the bus at Cleopatra?
Okay, well, that's maybe that will come in the next. Remember, the next section is conveniently called.
Oh, there we go. I mean, it's just, I'm perfect.
Yeah. Somebody else. Oh, you have a question.
Yes, well, it was more a general observation of your talk. I had the feeling that your goal was to present the various kinds of skepticism on a scale, a realist scale.
Yeah.
Which is very surprising as a project in a way. You use a realist scale to measure the various degrees of skepticism.
Right.
So it seems to be secretly or officially anti-skepticism. But that was my first remark. And then I saw that your scale has two facets. One facet of the scale is that it is determined by set theoretical objectivity, because you have this different steps which are connected with bigger and bigger steps, and then classes. So but there is another facet of your scale which is based not on the size of set theoretical entities, but which is based on syntactical complexity.
You mean the number of alternations?
Yeah.
Yeah.
So, but then, so I had this first feeling that that was your project to measure skepticism on a scale which has one facet which is grounded in set theoretical objectivity and its extension, and the other facet was syntactical complexity. And I thought that it's very much a ground tendency of contemporary mathematics. We have been so impressed by ZFC that we represent ourselves even philosophical positions with the scale. So I thought your project was an illustration of this. But then you explained to us this part about intuitions, and there was a common feature to all your intuitions, which is the Cartesian feature, which is every one of your intuitions is a clear and distinct conception, which was the Cartesian criteria for certainty. So I think it's a completely different atmosphere from the other facet of your talk, which I was first describing. So just this observation,
Okay.
Which is completely kindly.
Right. Thanks. Yeah. I mean, you could ask. Maybe this will come out later. That why do I ask questions about bivalence at all? Why not just start out by saying, do you believe in the reality of natural numbers, and do you believe in the reality of 2 to the nth and so on? I think that if I ask those questions, people would be, the audience would be quite mystified. And there's an issue there which maybe we'll come to later. I think it's really the bivalence questions is sort of way into this issue. It's certainly not that these positions are just about bivalence. Like I say, we're not. I don't accept that we can be just truth value realists and that we just believe that sentences have truth values. But if I ask, do you believe in the reality, then what do you mean reality? So we'll have to come to that soon.
Yeah. I wanted to mention that we have another half an hour.
Okay. Well, maybe we'll get to section 5, maybe even 6. Okay, 7 we can definitely skip. Okay, right. So now we've got all these intuitions, and we have to consider which of them is reliable. So of course I can't answer this. I'm just going to give some thoughts. So first of all, each of these intuitions claims, I mean, they're speaking to us, and they claim to have access in a limited form to some kind of objective domain of reality. And so some people are going to say, well, how is that possible? How can it could be expressed this with the access problem. How can a human mind have access to this immense realm? And the idea is absurd. And I'm not going to, I can't really give an answer to this, right? I'm not going to answer the access problem, but I do want to make 2 points. One, I'm going to say Platonism is not essentialism. This is going to be probably quite controversial, and I'm not even sure I can really say it very well. And the second, so Platonism is not as extreme as you might think. That's the point I'm trying to make here. And also that if you do reject Platonism, you go to ultra-finite. So these are the 2 responses, but they're not really answering the question. I admit that. So the issue with essentialism is really fundamental. It's when I say we believe in the reality of the natural numbers, or believe in the reality of that, what does that really mean? And I'm giving a bunch of examples: Googleplex, NAT, rationals, complex numbers, sets of nats, or whatever it may be. And actually, the complex numbers, I deliberately mention it because that has interchangeable I and minus I. But in all cases, we can ask, what does it mean to believe in the reality? So does it mean that we really think that each natural number, complex number, whatever it might be, is sort of existing out there and has some kind of transcendent essence? I mean, as I say, I'm not doing a very good job of putting this into words, but this I want to call essentialism, that these numbers are out there. And this is not what I mean by Platonism, but it's really quite difficult to say precisely what Platonism is as compared to this. So this, again, like I said, everything here this has all been said before in different ways, but So we can define two ways of encoding the rationals into the natural numbers. I gave it 1, 2 in the paper, which I called red and yellow. And so if you take the number half, the red encoding is 18 and the yellow encoding is 19. Right. They're just pretty simple encoding, pretty arbitrary. Now, I would say what it means to believe in the reality of natural numbers is because via this red encoding, anybody who believes in the reality of natural numbers also believes in the reality of the rationals. And the same for the yellow encoding. So via the red encoding and also via the yellow encoding. And you really see this. I mean, you sometimes hear people say, I believe in the reality of that, but I have doubts about the real numbers. But nobody is ever going to say, I believe in the reality of that, but I have doubts about the rationals, right? You will not hear that. And you can't hear it because those two beliefs, reality of that and reality of the rationals, they are the same belief. They are not two different beliefs. They are the same belief. Now, if Platonism really meant essentialism, so, there was this thing out there, which is a half, well, it couldn't be equal to the natural number 18 and also equal to the natural number 90. That wouldn't make sense. So clearly, so that kind of shows that whatever we mean by Platonism, it has to be compatible with this fact of believing in the reality of that being the same as reality of Q. And that's not a definition, it's more a negative thing. So what I'm saying is, when we think what Platonism is, we have to be careful. So definitely mere truth value realism is too little. So with Platonism, we certain about let's say we're particularist, we have to believe that CH is bivalent, that it has an objective truth value. So that's a lower bound, but it's more than that. But on the other hand, this essentialism, that's too much. That's clearly not what Platonists actually do believe. You can see it from this fact. So it's somewhere in between, and I can't do a really good job putting it into words. Like I say, ultimately, it's an intuition, it's an emotion. I'm not very good necessarily being able to put that into words, but it's just worth noting that there is something which is too much, and this fact about natural versus rationals tells us something about what Platonism does mean and doesn't mean. So to some extent, if people are unhappy with Platonism, it may be that it's because they misconstrued Platonism as essentialism. And if they knew what it really was, which unfortunately I can't define very well, they would not be so unhappy. Now, I'm not saying this is true for everybody, but it might be true for some people who say that they don't accept Platonism. And this is one reason why it's really helpful to give the questionnaire as a question about truth values and not as a question about reality. Because if I say reality, immediately this idea pops up of the numbers out there, which is, let's say, this is not what we want. So that's why I use truth value, not because I think truth value realism is what matters. It's the intuitions that matter. Okay, so this is my first response to the anti-Platonist criticism. Secondly, if you reject Platonism, then that leads, I would say, and others have said, to ultra-finitism. So if you think there is this problem, despite everything that I've said, it follows that you have to doubt all these intuitions, and you also have to doubt bivalence and Go-Back, which is exactly what Marco said, right? That is the ultra-finitist view. Now, this is contentious because I have, maybe you don't speak to people who are finitists and constructivists, but I do, and they will always say, oh, I'm taking this view because I'm not Platonist. But that if they're against Platonism, they should go all the way to ultra-finitism. Finitism is not enough. And the whole argument that anti-Platonism, Platonism is impossible because we can't access this huge realm, it applies just as well to the Googleplex natural numbers as the Googleplex bounded numbers as the natural numbers, right? It's got nothing to do with infinity because this set is one which cannot be apprehended by an actual human or computer. Again, this is under certain assumptions about physics, which you may doubt. But anyway, so that means that if you're going to take this anti-Platonist view, you go all the way to ultra-finitism. Those are my two responses to the anti-Platonist critique. I'm not really answering it, but Okay, so what I'm saying is that if you believe in the bivalence of Googleplex Go-Back, you might not, but if you do, because I don't think you can be a truth value realist, that means you are a Platonist. So I want to say, welcome to the club. Okay, that's my that's nice.
I believe that I am Platonist. I do not believe in that. Okay, so I am a very strange Platonist person.
Okay. But this was on the assumption that there is this computer that you that
No, I think that you say we have the notion of natural number is a clear notion, so blah 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 blah. Or you say that the notion of set of natural number a clear notion, etc., etc. But what does it mean that for us the notion of natural number is a clear notion, and we understand what mean? It means simply that we identify the generative process, and we consider that this generative process can be continued in the infinite. Good. Then, in order to formulate your conjecture, your statement, we need more than that. We need also multiplication and addition. So what we do, we give a definition using quantifier of multiplication of addition. A quantifier, we don't know exactly what does it mean, because we simply have the logical symbol that satisfies certain deductive condition. But intuitively, we think that this is valid for all the process that we imagine continues up to the infinite. But then we discover that with the means that we have to control this recursive process, we cannot prove some things. So we cannot prove something. So what does it mean that we believe that this is true or false? Because our intuition what natural numbers are depends on our, you want to use your term, your belief that it is finite intuition that we have with the capacity of producing is produced up to infinite. But then we discover that the way in which we can control it does not tell us enough tools in order to tell what happened after a certain moment. And so it's not more clear what does it mean, the reality of natural number. The comprehension of what natural numbers are is not the same thing as the belief in the reality of natural number. It's the belief in the fact that we can control our content with the means that we have. And the means that we have do not allow us to prove these theorems. So I cannot say much more than that.
Okay, well,
The other thing is metaphysics.
Let me come
It's
back.
pure metaphysics.
Let me come back, because I will talk about knowability in a bit, but not that it will absolutely, not that it will satisfy you, but I'll say a bit. So if we're not ultra finitists, which of course some of us may be, but if we're not, that means, so I'm saying we accept this set, the Googleplex that means that we are Platonists to some extent, up to that boundary. But then we have the question of how far we go. We've got to make this decision. We've got these intuitions, how far should we go? And I'm certainly not saying that this is an arbitrary choice, not at all. There are really profound differences between the intuitions. So, with the Googleplex in principle, it's a big word, but anyway, you can grasp the whole set. With natural numbers, you can't grasp the whole set, but you can grasp each one individually. With the sequence, you're giving one choice at a time, whereas with a function, you're giving many choices all at the same time. So these are very different intuitions. So it's totally reasonable to draw a line at some point.
I think that there is I will not say a confusion, but a difference that you do not appreciate now. One is to understand something intentionally, and the other to understand something extensionally. Intentionally understand all these notions, all of them, perfectly. What I do not do is understand them extensionally. So I do not know exactly what my intentional comprehension allows me to say about all of them. That is the problem. And so I intentionally, okay, all this is correct, but that extension I want to say with my intention definition, what I can prove. This is, I believe in what I can prove. I believe in what I have proved. Point. I don't believe in any other thing. Because my only understanding is intentional, is not extensional. I don't know what is the totality of natural number. I know what does it mean to be a natural number, that are completely different things.
So, I mean, in a way, it to some extent, I mean, I'm as I say, I mean, I'm not going into a lot of finer distinctions between different schools. And you could say, you know, the finitist does believe in the natural numbers in a certain way, but not in
A
the.
finitist, according to me, think that all what is finite can be accepted. It's not my case. I can accept infinite statement if I'm able to prove it with the means that I have at my disposal. But this means that I have at my disposal are the means that depend on my intentional understanding of natural number R, not on my extensional understanding. And my extensional understanding is simply I don't know what it is. I have no extensional understanding of infinite. I have an extensional understanding of finite, a very small one, 100, 150, 200. But intentionally, I have an understanding of infinite. Simply with the means that my intentional understanding gives to me, I can prove something extensionally, or I cannot prove other thing extensionally. So I only believe in what I can prove, which this thing means. The other, I have no belief. I don't know what it is. Give me a proof, and I believe you. You have no proof. He asked me whether I believe or not. I don't know. For me, it's simply nonsensical question. Whether I believe or not is something that I have not a proof. Because what I understand is only what is a natural number, not which are the natural numbers.
So that I think, I mean, that sounds more in line with a finitist point of view.
If you call finitist, let's say that I'm finitist. I may not believe to be finitist, but if you can make me finitist, I am ready to accept this idea.
Okay, I think maybe the point I'm making is that somebody who draws the boundary of so let's say somebody who draws the boundary before bit streams doesn't mean that they think the whole concept of a bit stream is rubbish. It just means that they don't feel that it's clear enough that you can quantify over it and get a truth value out. But they may still be able to do some kind of reasoning about bit streams. I'm not going
There are a lot of infinitary statements that are proved, and so I believe in them in a certain sense. If we say for any natural number nm, the addition of nm is identical to the addition of mn, there is a commutative. So it's an infinitary statement that I have a perfectly proved it. The means that is given to my intentional definition of my intentional understanding of natural number or additional natural number allow me to prove it. And I have no problem to say that all the natural numbers satisfy the condition of commutativity of addition, because I have a proof of it. So it does not depend on how much far you go. Depends on what you can prove using the means that you have.
So I mean that definitely, that would definitely be provable with a finitistic theory that addition is commutative. The fact that but I will I mean I will talk a bit about knowledge in a bit. Then that will
Okay, I stop because otherwise.
Okay. All right.
That's
How we do right. So
But I have to say that it's a really pity that to skip all of that, because even if I think that I disagree practically on anything that you say, I appreciated a lot of your talk. I think that this seems really something that makes us think. So I really would like to go on any word of what you say, because I like it very much.
okay.
Or what you say, not because I agree, but because it makes me think.
Okay.
It is exactly what a talk should do,
Right.
make someone think.
Okay. Good. Okay.
But the problem is that we cannot stay here up to 9 o'clock.
I thought it was going to go to 6:50. But not.
6,
6:50? No,
6.
about 6 or 6.
Almost already at 6.
Okay, that was the advert, so that's what I received. But
Oh,
Oh, it's 50 minutes.
sorry. Then
oh, was that a mistake?
there was
Okay,
something up.
that's what I kind of was.
Okay, I have messaged my kids, according to what we can say, I can stay here up to 6 half or no. I come back.
Okay.
It's a vocal message. I am a slave of my kids
Okay.
and my wife too, but that's another story.
Okay. Yeah, I was told it was 2 hours 15 minutes. Okay, so waiting for Marco to.
No, please continue. Yeah.
Carry on. Okay. Right. So we've got all these different choices. So I mean, I at this point, as I say, we have to make a decision how far to go. We've already discussed a bit about ultra-finitism versus finitism. I'm going to skip several steps forward, really relevant to the talk because this is where we started with. question of arbitrary functions. So I suppose we're happy with natural number and we're happy with sequence. Are we going to go on to the next step and accept arbitrary function? And there are two reasons that I've already mentioned that people give why we should not. One is these independent results, which supposedly is a reason we should think we should doubt the bivalence of continuum hypothesis. And the other is Balatoski, which supposedly is a reason we should doubt choice. So I'm going to make some argument against these reasons. So as far as the independence issue, I mean, I have to say, I don't understand this, why independence should be considered a reason for doubting bivalence. I mean, you know, even if we cannot know whether Cleopatra ate an even number of grapes, I don't see why that would be considered an argument against bivalence. So I really don't get this at all. But
one is reality, and the only mathematical reality we have is given by our theory. And if we have various good theories, then
okay, but I'm saying we believe on the basis of these intuitions. And if the intuition is strong enough, so okay, so let's carry on for a bit. Maybe it's, I don't know, it's made address probably whether you're happy, but anyway. So of these intuitions that we've said, none of them ever, you know, they were very naive. They're these little people who know very little, right? They just claim to know the most basic properties about natural numbers, for example, or sequences, nothing more. I mean, if you think all the things that we know about natural numbers, and we know a lot, most of that comes from proof. It doesn't come from the intuition. So whatever, you know, we may have limits on what we can prove about natural numbers, perhaps we do, but why should that say anything about the reliability of the intuition? I mean, the intuition, you know, contributes a small amount from which we then do all this fancy stuff with proof, which is not intuitive at all, not at least in this sense of intuition. And why would that be a reason to doubt, to say that imagine, the pessimistic scenario, we can't resolve twin prime or whatever. Is that a reason for saying that twin prime, that this intuition, that a natural number is unreliable? I don't see that. So I'm basically just saying that I don't follow it, but really it's not, you know, people say, well, there's something flawed about our intuition that we can't, about, you know, bit streams or sets of bit streams, that we can't resolve the continuum hypothesis. Why? I mean, this is condemning that intuition for something that, not doing something that it never claimed to do. It never claimed to have all this knowledge. It just told us a few little things that it claims to perceive. You know, we can accept it or we can not accept it, but I don't think, I mean, to me, the big difference with belief in natural numbers and belief in sets of bit streams is belief in natural numbers is a much stronger intuition. That's something that I'm accepting, and I'm saying for sure that your belief could depend on the strength of your intuition. But
sorry, the reason for which Cleopatra statement is unknowable are essentially different than the reason for which the continuum hypothesis could be unknowable. Because in principle, if we were able to come back temporally and to take a note of any grape that Cleopatra had, this is perfectly knowable. So the reason for which is not knowable is simply physical reason, that we will not come back in time.
yeah,
But the reason for which continuum hypothesis is unknowable is not physical. If it were unknowable, is pure abstract. So the situation here is completely different. In a certain sense, the Cleopatra statement is factually knowable in principle. Simply I cannot do because my human capacity are very limited. But I cannot. But I can imagine a being that is able to come back in the time and to stay close to Cleopatra and take a note of any grape that she is. And so for this being, this is perfectly knowable.
okay, so for me, okay, this is interesting. What you said is interesting because, to me, the bivalence of the Cleopatra hypothesis, I mean, I do think that it's bivalent, but my reason for believing this has nothing to do with an imaginary being going back and counting all her grapes. It's just a belief about the past, that it is real, And I don't need
No, I don't speak about I speak the reason for which is not knowable.
Yeah,
I'm speaking knowability here.
right.
Because on the reality, yeah, I agree, because this is a fact, and
Right.
I have no doubt about its empirical existence, so certainly
Right.
is a matter of the fact.
Okay, okay.
The fact that Cleopatra had even or odd number is a matter of fact. I totally agree
Okay.
with you.
Okay,
Now, but this matter of fact is not, we cannot know it.
yeah,
Why we cannot eat? Because of physical restriction, not because of intellectual or a priori restrictions. And in the case of continuum hypothesis, if it were unknowable, still we don't know, but if it were unknowable, it would not be unknowable because of physical restriction. It would be unknowable because of a priori reason. So the situation is quite different in two cases.
but the question of whether this is an
No.
argument against bivalence still arises. I mean, the question is, why should unknowability be an argument against bivalence? I'm not saying it's not an argument for, but it's but why should it be an argument against bivalence if that's what I don't get.
Exactly, because instead, in the case of Cleopatra, I think that there is a matter of fact, independently of my capacity to know it. And I can also imagine that I can imagine a being that is able to know this matter of fact. So the matter of fact as such is not intrinsically not knowable. In the case of natural number, there is no matter of fact.
So
I don't see what should be the matter of fact, except if we were essentialist.
just
The only way to think that there is a matter of fact is existentialism. And that I do not believe in essentialism. I agree with you. But Platonism is not essentialism. I totally agree with you.
okay.
But I do not see any other form of non-essentialism that can accept the idea that there is a matter of fact about the continuum hypothesis.
At least in your talk, your argument is sound to me, because bivalence is something that you introduced in order to have something beyond unknowability.
Mhm.
So
Yeah.
the way you say it, it works
Yeah, but also
for obvious reasons.
other point, yeah.
That's right.
Well, the other point I want to make is, I mean, I said here, suppose we're accepting arbitrary natural number and arbitrary sequence. So for me, you know, if you are, I mean, if I'm speaking to somebody who doubts the bivalence of Google Thorbat, for example, I wouldn't discuss continuum hypothesis because there's no point. Remember what I said, that once you say no, that's the end of the questionnaire. So wherever you say no, I'm not really interested in discussing the more advanced, the more, you know, the more, whatever you call them, the later parts, because it's almost pointless. If somebody is a counterbalist, then I'll talk to them about Littlewood conjecture. I'm not going to talk to them about continuum hypothesis because it's too far forward. Let's talk about the boundary, because then it's a reasonable discussion trying to get.
Your reason, assuming the point that this difference of belief depend of how strong is the statement, in some sense of strongness. I don't think that this depends. I think that all of them are exactly analogous with respect to my possibility of believing or not believing them. It's not because one is a sigma one or not like P or sigma. I don't remember whether it's P or sigma.
Yeah.
Sigma one, sigma two, sigma three, that my belief between them can change.
It's part
No,
of what
because
I said.
intentionally speaking, I understand perfectly all this notion, all the notion of set, the notion of set of set, the notion of set of set of set. I perfectly understand. So in a sense, I believe in all of them. In a sense, I believe in no one of them. So it doesn't, I don't think the scale is very relevant from this point of
It
view.
gives some realist value to the scale.
Sorry?
Yes.
His point of view gives some realist value to the scale.
Yes.
It's obvious.
Yes.
Because I agree with Marco, classically, every mathematical object was dubious.
Mhm.
But now we have the feeling that some may be doubted and other more difficult to doubt. And we adapt this to the scale, which means that the scale has impressed us so much.
Okay.
Yes, I agree, but I am not impressed by the scale.
I know.
The difference between you and
You never were.
Okay.
I think that the problem that we have in the end of the scale, we have exactly the same in the bottom.
But I
The
think
beginning.
the talk is marvelous because it shows us
I
how
see.
we relate to the scale.
Michel, I said that I disagree with what you said, but I said that anything that you said makes me think.
Yeah.
Because of course, the position that you present is a very relevant, interesting a fruitful position. It's not my position, but what is the problem?
Right.
Sorry to comment.
Okay, it's fine. I don't know how long I've been going on, but anyway, right. So right. So I've already made this point, right? So the intuitions, they speak to us and they don't claim to know very much. So if they are indeed ignorant, it doesn't count against them because they never claim to be knowledgeable in the first place. They only claim to know a little bit. And okay, that's what I have to say about the independence. Do you agree or not? As far as the Banach-Tarski is concerned, I can't say very much. I mean, this is the idea that somehow we have to reject Banach-Tarski. That is based on geometric intuition. This is something that mathematicians used to believe a lot more and became more distrustful of over time. And also, you had arguments to be made that there are also theorems without axiom of choice that violate geometric intuition. So that I can't really say more than those 2 points. So even if we don't accept those 2 arguments, the independence argument and the Banach-Tarski argument, we still have this question of whether to accept arbitrary function. I mean, I personally feel it's strong enough to accept, but I do, I have some ambivalence. I can understand why other people would want to be more cautious. As I say, I don't understand why people would take in those 2 arguments, especially the independence one, but I do understand the sort of I do see that the intuitions get weaker as you move along the scale. That I certainly feel. Again, it's a feeling. I'm only describing my feelings. That leaves one intuition we haven't discussed, and this is arbitrary ordinal. Now, this is highly controversial. A lot of people have argued about this because now we're quantifying over all ordinals. Now, remember what this intuition said. It said, I perceive a notion of ordinals that is as liberal as possible, and yet we've got this thing that we're quantifying over, which is order. We're saying this is really clear, really precise, so it has an order type, and yet that is somehow excluded from this range, and that is Baradi-Forty paradox. And it really makes it hard to believe this intuition, and that's what personally, and like many other people, I'm skeptical about this intuition. I don't accept that. I don't believe in the bivalence of GCH.
You have something about the quantification of all ordinals,
Yes.
but you would not of all cardinals.
No, well, cardinals also. I mean, they will be equivalent. Yeah. So it's assuming choice, which we've got past choice, right? Once we with choice.
Yes. Okay. So cardinals are ordinals, but not all ordinal cardinals. So
That's right.
Imagine
They can be encoded as each other. I mean, if you accept cardinals, then you could define an ordinal to be a cardinal together with a well ordering on that cardinal, and therefore, so it's similar to what I said about rationals and naturals. Belief in the totality of.
I did not know. You can encode. There is a bijection between cardinal and ordinals. Oh,
Yeah, sure.
Yeah, with choice.
Rejection?
With choice, there is.
Yeah, with choice. Yeah.
Sure. Because you can number the cardinals.
Yeah, you have bijection.
Right, so that's the
in fact,
bijection.
forget what I said about well ordering. Yeah, just numbering them is fine.
okay.
Because it's a class function, but
Yeah, sure.
So a problem that I have here, and unfortunately, we haven't let you talk enough about consistency, maybe to answer this question, but isn't GDN equiconsistent with ZFC? And
That is true.
Yes.
And so why don't you believe? You should at least believe all of the order theoretic statements that GDN.
So are we talking about believing in bivalence or believing in truth? Sounds like you're talking about believing in about theorems rather than believing about bivalence.
Yes, but then wouldn't it be strange if only the provable statements, only the provable order theoretic statements are bivalent and the other ones aren't? That seems like the kind of issue that you're trying to.
Okay, I'm not. I didn't say. I didn't really say anything about ZFC at the moment. I mean, I didn't talk about about this theory. I'm just talking about sentences, or particularly the sentences in the questionnaire, right? So I'm saying I accept the bivalence of continuum hypothesis, but I doubt the bivalence of generalized continuum hypothesis. Again, other people have said this too, right? It's not terribly original. Exactly because I accept the intuition of arbitrary function and arbitrary natural number, but I doubt the intuition of arbitrary order. It feels very unstable to me. I can't, this ordinal that's as liberal as possible. I didn't see the connection with that conservation theorem, which is true. You're right that MBG is conservative over ZFC. But how
Yeah, so I guess I was kind of taking that like, oh yeah, if you accept like axiom of choice, then you're probably going to accept ZFC, but I guess you've been couching it in terms of Z3, so
Right.
sorry.
Right. No, this is definitely a good point. But so no, I'm not saying that I'm accepting ZFC, not at all. I know, and third order arithmetic, yes. But
Yes,
sorry. With choice. Okay, so totalists, they do accept arbitrary ordinal, but the problem they have they of course are drawing the line at a different place, the class theoretic sentences. The problem that they have, if you ask them, is pretty similar to this problem. I mean, they're basically saying, well, quantifying over all classes of ordinal, but what is a class? I mean, ordinals are supposed to be as liberal as possible, so it's confusing, unstable. It's like, I think Maddie had this phrase, you have this extra level of ordinals that we forgot to add or something like that, forgot to include. Anyway, so it's a similar idea that totalists have their boundary. Okay, so now we have a summary of what we've had so far. So we started, I think this is actually the start of the next section, which is consequences of belief and doubt. Yeah, I'm just going to keep talking until you tell me to stop, basically. Sorry, that's an empty room, it's fine. You can all be having a nice dinner and I can be talking to everything. Right. So we started by saying that we only accept proof and intuition, not inductive evidence. And I listed, some intuitions that I experience, and also I'm assuming that aren't others that you might have because that could undermine my argument. And we looked at which ones are reliable. We saw various ways of answering this question. And now I want to consider the consequences. So if we accept the arbitrary natural number intuition, extensional, as you put it, that's the intuition. We believe in this platonic realm of natural numbers, whatever that means, and I don't want to, it's not essentialist, but in some sense we believe in that. And certainly we believe in the bivalence of every sense statement, arithmetical sentence. That means that we believe each axiom individually and every instance of an inference rule. So each theorem, once we've seen the proof, will be acceptable to us. Now, I have to make one more little bit of assumption. If we are able to reflect on our reasoning process, which is something that luckily everyone working in this field is able to do, then we can see that we're going to accept every PA theorem, and we're going to accept that PA is consistent. Just from that intuition combined with our ability to reflect on our own reasoning. Without that reflection ability, we would not get to complicate what we start with. Right. On the other hand, if we doubt arbitrary natural number, that means we're finitist, then this particular argument for consistency isn't going to work because we don't have that intuition. But maybe there's some other proof that's going to convince us that the famous, this is Hilbert, right, the whole Hilbert program. Maybe there's another proof. And indeed, there are two famous proofs. There's the proof using induction at zero, and there's a proof using higher order constructions. So if we accept one of these principles, we're fine. And in fact, there are a whole lot of people who do kind of finitists who accept higher order constructions. They're called constructivists. So they're okay. They will accept consistency. But if we don't, then we have to doubt consistency. According to what I've said, because we have no reason to believe it. We don't accept inductive, we don't accept the clever people argument. Forget that. We need a proof or intuition. We don't have it. We can't even Googleplex consistency. We can't accept, right? It's the same reason. So that's where we are if we're a fanatic. Okay, let's move on. It's the same story again and again. Maybe this will get boring after a while. So if we accept arbitrary sequence, then we're going to believe in consistency of Z2. But if we doubt it, so we're at the counterbalist point in the spectrum, then we don't have that argument. Maybe there's some other proof, and there are two in the literature. So there's the Tate and Girard proof, which quantifies over all sets of natural numbers. Well, that's exactly the kind of quantification we don't believe in, so that's not going to work for a counterbalist. And there is this other technique using higher type bar recursions. Maybe we would accept that, but I think that's quite unlikely. Yeah. But otherwise we don't, then we have to doubt not just consistency, but Googleplex consistency of second order arithmetic. It follows because we haven't got any reason to believe it. Just default position is doubt. What about Z3? So let's suppose now we're accepting arbitrary sequence. If we go all the way to arbitrary function, again, if we can reflect, then we believe in consistency of third order arithmetic. If we don't, that is, we're a sequentialist, we don't have this path to consistency. So what proof could there be? Let's check the literature. We find that Pravitz and Takahashi did prove it using some quantification that this sequentialist is definitely not going to accept. So that's pretty useless for us, but in this purpose, I don't mean the proof generally is useless, but for its particular situation, it's no good to us. So we have to doubt, this was my headline, remember? If we doubt arbitrary function, then we have to doubt not just the consistency and even the Googleplex consistency of third order arithmetic. And I'm saying there is no middle ground here. There's no other reason we can appeal to accept, believe in this consistency. So now this is really the center of my point about the price of skepticism. Yes, we can accept or doubt an intuition, but what we can't do is half accept. I mean, I'm happy to have different sections of our mind that, you know, believe different things. That's fine. No problem with that. But we can't have one part of our mind that half accepts. If this part of my mind thinks that arbitrary function is an unreliable intuition, it discards it. It can't rely on it anymore. It can't use it in an argument. So therefore, we have to doubt consistency. Again, you could say, you know, think about, okay, people here know history much better than I do. But anyway, so maybe, you know, mathematical community came to see geometrical intuition as being unreliable. And after that, you could no longer appeal to geometrical intuition and approve. Again, if you don't agree with my history, that's fine. Okay, so I've talked about bivalence, and let's talk a bit about choice. It's the same thing. I said that arbitrary function includes the belief in choice. This is what my description of my intuition. So that means that if Banach-Tarski theorem isn't objectively true, if it's less than in some way, objectively true statement, then one of these intuitions, maybe both, is unreliable. And that means Googleplex complexity of third order arithmetic, we have to doubt it, right? Because we haven't got those two things that we needed to support it. The support for that belief has been taken away. We've doubted, came from the intuition. And of course, that also applies for dependent choice. That was part of the arbitrary sequence intuition. So if we don't doubt dependent choice, not that people generally do, but if you did, you would also have to doubt second order arithmetic consistency and Googleplex consistency. It's just the same story again and again. Okay, so we've been through this. We've come to the headline. I've said that if you doubt the bivalence of continuum hypothesis or the axiom of choice, you should also doubt the consistency of third order arithmetic. And this is the case that I've made. So at least if I have to stop at some point soon, which I possibly do, then at least I've explained the price of skepticism, right? If you don't accept the intuition, if you don't believe in the reality, whatever it means to believe in the reality, it certainly doesn't mean essentialism, then you also have to doubt consistency, because we cannot accept this clever people argument. That's not something that is, you know, we can go with.
So we are started to go up to 9 o'clock, so let's go. You repeated the same argument at different times. So
Yeah.
can you explain me this argument only in one occasion? So the way the structure of the argument was not completely clear.
Okay, so I'm saying that we have some intuition.
Okay.
We have to for each intuition, we either accept it fully or doubt it fully, but there isn't an in-between. That's the key point. So if we accept it fully, that gives and we have the ability to reflect with an extra ability, then we get an argument for consistency.
Which argument?
The argument that says that each axiom is true and each inference rule preserves truth. And that's an actual argument from truth, right? But if we don't accept the intuition, then we have to doubt the consistency statement because we don't have any reason for it. And by default, if we don't have a reason to believe, we doubt. That's the argument.
Okay.
And again, this has been
Again, you're not claiming that it means it's inconsistent. You believe it's
Absolutely not.
inconsistent.
I'm giving you
Absolutely,
no
it's
argument.
only doubt. It's only,
Yeah,
yeah.
just an absence of belief in consistency.
Right.
So that's my position. Maybe I should stop.
Doubting the hustle.
So the only argument I have to believe in consistency is even the bivalence of relevant state.
Okay, in this case, it's No, it's not the only argument, but we looked at some other arguments and we rejected those too. But it depends on the case. In some cases, like piano arithmetic, it's different. It really depends on what proofs are available. So you have to look at the.
So let's take theta 2. No, the continuum hypothesis requires theta 3.
Z3, right. So then.
Let's equate theta 3. So I doubt about the bivalence, not me, but someone, X, doubt about the bivalence of the continuum hypothesis.
Yeah.
Then it cannot accept it cannot believe in the consistency of theta 3. Why?
Because they have no reason to do so.
Okay. And would be the reason to do so if X accepted the bivalence of continuum hypothesis?
Okay, it wouldn't be enough to merely accept bivalence, but I'm saying that the reason you would accept bivalence is that you accept these intuitions. And it's those intuitions that, together with the ability to reflect, that leads to a belief in consistency. But I should say, I mean, the
Okay, let's see.
Can one have an intuition of consistency?
just by itself.
Yeah. Instead of having an intuition about the axiom of choice, an intuition about the.
I don't see it. I don't see how one could believe that if you didn't believe in all the to have an intuition, for example, to have an intuition.
For example, have a belief that CFC is consistent. I have this belief. I truly believe it.
But without having a belief that
I don't have any proof of it, and I don't think I will have ever a proof of it.
Okay, I mean, okay, so I mean, obviously that implies in particular that Z3 is consistent.
Yes.
I mean, ZFC actually involves some different issues that I haven't got into, so that's why I wanted to focus on the
but
easier one.
it's about I don't have my belief is about the consistency of a theory in that case, but I could have also the belief of the consistency of Z3 or.
Well, I mean, as I say, if you believe in consistency of ZFC, then you also believe in consistency of Z3.
Sure.
But you say you have that without an intuition that CH is bivalent. Like that's a separate matter?
Yes.
Okay, that's something I don't understand.
I don't want to continue this discussion longer than but let me just say it as short as possible. I have an intuition of what sets are. And then I try to form a theory that formalizes this notion of sets. Some things I can think as reasonable, like if I have two sets, I can construct the union of these two sets. So I accept the axiom of union. The axiom of choice is also of this matter, is I can accept that I can make choices if I have a family of non-empty sets. But once I have this theory that I formed with those axioms, then you tell me, okay, in that theory, I can construct an object that is the real numbers, and I can construct, and then I can construct sub-objects, subsets. Do you believe that there is a bijection between these two things? Then I don't have any intuition about that. I had intuitions about sets. I formed my theory about that, but I don't have any intuition about the continuum hypothesis. I mean, none at all.
It is exactly.
But the thing is, you don't need. I mean, I don't have an intuition about whether continuum hypothesis is true or false. But
I don't know if it is by balance or not.
That's what that. Okay, but okay. I mean, leaving aside ZF and just focusing on third order arithmetic, which is much simpler.
Yeah.
Right. I mean, it's the theory that you're setting up has got these quantifiers.
Yeah.
So if you don't think that those quantifiers are ranging over something clear, what is making this theory meaningful?
Well,
to you?
you think that CF3 is simpler than Zemmel-Frankel?
Yeah.
Because you can prove the consistency of one from the other.
One is it's more than that. One is a
but
subsystem.
to me, Zemmel-Frankel is simpler than the other because I have an intuition of CF3 because I work in CF3, but I don't have an intuition exactly of what is true or it's not true or how the arithmetic works. I do not have an intuition of that. Exactly. I have intuitions about sets.
Exactly. This is exactly my point.
Well, I mean,
talking another way.
The truth is, Woodin is saying exactly like he says.
Sorry?
Woodin, he says exactly like Paul is saying, because he says that the domain is reliable So CH must be decided.
Well, I mean, but
It's
that,
bivalent.
but it's actually, it's not quite what I'm saying. I'm not saying that, I mean, if it's more, if you accept that the domain is reliable, is clear, then it becomes bivalent, right? But I'm not, but my point, although I personally, I'm a particularist, that's not what I'm preaching today. But I'm saying, sorry.
Yeah,
just
for
be-
you, say if we know the bivalence, then we have the domain, rather.
I'm saying that the only reason for believing bivalence is that one would have for accepting bivalence is some kind of is this intuition that the domain is clear.
Yeah.
But that's different from what you're saying. I mean, you're not accepting bivalence. So first of all, third order arithmetic is just a subsystem of ZFC. I mean, it's nothing more complicated than that. You just got natural numbers, sets of natural numbers, sets and sets of natural numbers. That's it. So it's very clearly a subsystem.
Yeah. But what kind of things are true about sets of natural numbers?
Oh, okay, so I didn't show you the axioms, but it's just extensionality and comprehension. There's nothing that if you accept ZFC,
but still, I do not know what things are true about that. I don't have any intuition about those subjects.
I do not know what
I have intuitions about sets, that's true, but I don't have intuitions about particular sets.
Exactly. It is the point. So they make the same with zeta 2. I have an intuition, if you want to speak about intuition, of the 5 axioms or 6 axioms, 5 axioms of zeta 2. Seem to me, all of them seem to be reasonable. I know I can I can imagine I could give a model of them by constructively defining a natural number. Finished. So I believe that is consistent. Then then I know that I can define addition and multiplication because I approve that the definition is appropriate. And so if there is consistent at zeta 2 and it can define addition and multiplication, I can add addition and multiplication. I can formulate a lot of theorems that use also addition and multiplication, and all these will be consistent because it's in any case a consequence of my 5 axioms that I believe to be consistent because I can have the intuition of the construction of a model of them. This does not mean that I have an intuition of totality of natural number. Absolutely not. Or even of all the statements that I can formulate about addition and multiplication of natural number. I have no intuition of that.
Shall I just finish this section?
Yes.
Section 6. I think that's like. I think maybe this is a good place to end because I think we're not going to have time to really. Only a few bit more on this, but so this distinction, we've done it all the way along the spectrum. There's also a theory of finitist arithmetic, which is called primitive recursive arithmetic. It's the same issue that finitists, as long as you can reflect on their reasoning, your reasoning, you can accept it's consistent. If you're an ultra-finitist, according to my argument, you have to doubt that, even multiplex consistent. And look, here are some historical examples. This is not a theoretical thing that I'm saying. You know, here we have a sequentialist who doubted third-order arithmetic consistency. We have, I'm not sure they're either countableists or you could say they're constructivists, but it doesn't matter for this purpose. They doubted consistency of second-order arithmetic. You have a finitist who doubted PA consistency. You have an ultra-finitist who doubted PRA consistency. So they all are historically witnessed. Well, obviously, that's not really an argument for anything, but interesting. And finally, this is the last part of this. So we could also consider dropping the law of excluded middle. Many people who are skeptical of various ways would want us to do that. We can drop excluded middle and also extensionality. I don't know if that makes you any happier. We can consider the theories without extensionality, but that does not affect consistency. So moving to intuitionistic logic and dropping the intentionality axiom does not help us to achieve consistency. So I would say that if you have to doubt the consistency of the classical version, you also have to doubt the consistency of the intentional intuitionistic version, right? It doesn't help. You might think it would help, it doesn't. Okay, that's kind of the end, right? That's the end of section 6. So I will skip section 7. Very interesting. You're not going to hear it. So I'm not got time. Sorry about that. And then, okay, there's a little bit of discussion about I've only talked about what sequentialists should doubt. I've only preached to other people. I've not preached to myself, right? So this is really suggestions for what particularists and totalists should doubt. And okay, the conclusion is exactly the same as the first slide, pretty much. Yeah, so we have we make our decisions based on the strength of intuition and our degree of caution, but we have to line up all of our beliefs. And what we can't do is believe that theories are consistent without believing that they're real, which obviously you're not agreeing with. And so the summary is that skepticism comes at a price.
Thank you. Thank you.
In the beginning of the seminar, we said that there were three different sort of speakers: the physicist, the mathematician, and the philosophers. Physicist speaks 45 minutes. The mathematician 1 hour, and the philosopher 1 hour and a half. Now we have the ultra philosophers.
I'm in a computer science department, so then you know.
Thank you. Thank you very much. We believe in all this.